Okay, let's go ahead and get started today. Today we are going to cover something similar or related to what we covered last class, but today we're going to be doing a different kind of conversion. We're going to be converting from a DFA to a regular expression. Now, as a quick review of conversions between the three different methods of defining languages that we've seen, any regular expression can be converted into an NFA. We did that with that kind of replacement method where we started off with the primitive regular expressions, replaced those with an equivalent NFA, joined, and every time we saw one of the composite regular expressions where we had a concatenation or a union operator or a star or a plus, we replaced that with a certain form of NFA. And we just kind of repeated that through the process of the entire regular expression until we had the whole thing converted to an NFA. And that NFA is guaranteed to represent the same language as a regular expression. And then we said, well, any NFA can be then converted to a DFA using that kind of subset construction method, where you basically say, what are all of the states I could be in after this symbol? That becomes its own kind of meta state that has substates inside of it, or a collection of states inside of it. And we do that through the entire thing. We use that table-based method for that, where we would eventually fill up the entire table. And then we just relabel those as new states, and then we have a DFA. And incidentally, all DFAs are a restricted form of NFA, so their DFAs are all also NFAs to begin with. And so, but that's not sufficient. What we've done so far is not sufficient to prove the equivalence of all three. And why not? And the reason for that is, right now, we can go from a regular expression to an NFA, and an NFA to a DFA, but notice we don't have anything that gets us back to regular expression. So there might be right now a DFA that we couldn't make a regular expression for, even though every regular expression we can make a DFA for. So right now we have no way to get from NFA or DFA back to regular expression. And that's what we're going to do today. We're going to fill in this kind of part of the triangle and get from DFA to regular expression. And if I have that, notice I can now get to any part of this, any representation from any other one. If I have an NFA and I want to get to regular expression, take the NFA, make it into a DFA, turn the DFA into a regular expression. If I want to get from DFA to regular expression, just go straight there. If I want to go from regular expression to NFA to DFA back to itself, we could certainly do that. And one thing that's important to note here is there's more than one NFA that defines any given language. There's more than one regular expression that defines any given language. In fact, there is an infinite number of regular expressions, or NFA or DFA, that define some given language. So if you go regular expression to NFA to DFA back to regular expression, you might get a different regular expression out than the one you started with, but it'll be guaranteed to be equivalent. They'll define the same language. In other words, you could manipulate one using those algebraic properties to get it into the form of the other. All right, so let's fill in that missing conversion today. This one over here. That's what we're going to focus on. Okay, so here's a DFA. And first off, let's just make sure that that is a DFA. It's got a finite number of states. It's got an alphabet of A and B. Every state, therefore, DFA having to be a total function, should have an A leaving and a B leaving it. And Q0 does. Q1 does. There's an A. There's a B. Q2 does. There's an A. There's a B. And it has a final state Q2. So that's definitely a DFA. No lambda transitions, no multiply defined edges leaving any state, and it's a total function. So what we want to do is we want to convert that into a regular expression. So step one is to add a new start state and a new final state. And we're going to call those S for start and F for final. So notice what I did is I just connected S to the original start state on a lambda, and I connected any final states of my DFA. In this case, there's only one. It's only Q2. We connected that to F on lambda. If I had more than one final state, I would connect all of them on lambda to this new final state F. And the reason that we're doing that is that isolates the kind of DFA in between S and F. And then we're going to start reducing that and eventually replace it where S goes to F on this regular expression. And notice this did not change the language. This has now made this into an NFA because we now have lambda transitions with the DFA kind of trapped between the two. So it's guaranteed that that represents the same language, hasn't changed the language at all. But we've now isolated all of these kind of parts of the DFA between the S and the F. So if we can reduce those and get rid of those, and replace that with a regular expression, that's what we're going to do. So step 2 is going to be to choose one of these states, and it really doesn't matter which one we start with. We could really pick any of them. We're going to choose one, and then we're going to reduce that. So step 2 is to eliminate a state by accounting for all incoming and outgoing edge combinations. So in this case, we're going to choose Q2. So here's Q2 over here. So looking at that, what are all of the places that we could come from to get into Q2? And then what are all the places we could go to leaving Q2? So notice that we're not going to count this A that stays there. That's going to end up being like A star, so 0 or more. But coming into this, we can come from Q1. There's only one incoming edge, and that's from Q1. And then there are 2 outgoing. There's one going to back to Q1, and there's one going to F. So we're going to represent those. So we have Q2 is always going to be in the middle here. So we can come from Q1 through Q2 on our way to F, or I could go Q1 to Q2 on the way back to Q1. And notice on our graph over here, Q1 into Q2 on the way to F, or Q1 into Q2 on the way back to 1. So those are our 2 things. Now, what we're going to do is we're going to label over the top of these what it takes to get us from Q1 to Q2. And if we look at our graph over here, from Q1 to Q2, that's on a B. And then what does it take to get from Q2 to F? That's lambda. What does it take to get from Q2 back to Q1? That's another B. So we're going to label those over the top. So in other words, Q1 to Q2 to F is a B. So it takes a B to get us into Q2. And then A star is while we're in Q2. Anything that loops back, we just put a star around that. And then on the way to F, we would then use lambda. So notice to get from Q1 to F, it would be B, A star, lambda. And so there we have B, A star, lambda above that one. Now what about Q1 back to Q1? Q1 back to Q1 is B, A star, and then B. So now that we've labeled those, what we're going to do is now we're going to replace the Q2. We're going to eliminate it. We're going to get rid of it entirely. And we're just going to say, well, we know what it took to get us from Q1 to F. It's B, A star, lambda, or just B, A star. So we're just going to get rid of Q2 altogether and just put an edge from Q1 to F and label it B, A star. And we're going to put an edge from Q1 back to itself. It's going to be labeled B, A star, B. All right, so there we have it. So there we have B, A star, lambda, which is the same as just B, A star going from Q1 to F. And then we have Q1 already had this A looping back, but we'd added another loop back, which is B, A star, B. So now we've completely gotten rid of Q2. So now we're going to repeat that, and we're going to eliminate another one. So let's eliminate Q1 this time. So now Q1, notice it only has one way in and one way out. So in this case, it's going to be Q0 to Q1 on the way to F. So Q0 is an A coming in, so we're going to put an A there. And then what about staying in Q1? Well, the things that loop back are going to be A or B, A star, B, that whole thing star, because anything that loops back we combine with an or. And then that becomes something that's in the star. So there's the A looping back, there's the B, A star, B looping back. We put a star around the whole thing. And then leaving Q1 going to F, we have B, A star. So now we have this. So now we're going to get rid of Q1. We're going to eliminate that and replace it with this expression. So Q0 to F is going to happen on A, and then parenthesis A or B, A star, B, that whole quantity starred, followed by B, A star. So we've replaced that, and there's what our edge is labeled now. Now we've only got one state left to eliminate, which is Q0. So here we just brought this to the next page. And there's only one way in, that's from S, and one way out, and that's to F. So now we have a lambda coming in, B star staying there, and then this whole thing going out. So there's the lambda coming in, there's the B star staying there, and there's the whole thing coming out. So now we can redraw that without Q0, and we're going to get lambda B star A followed by that whole thing there. And that lambda at the beginning, we can get rid of that because that's not adding anything to it. So here's what our final step of this is now that we've eliminated all the states, the edge that we're left with is just going to be, or between S and F, the label that's on that is going to be our regular expression. So we just got rid of that lambda and have this. So here's what the DFA looks like. Here's a regular expression that represents that same language. And as kind of an idiot check here, you can kind of see here's B star A followed by either an A, or A or B, A star B, that whole thing star, followed by, how do I get over here? B, A star. And so you can kind of see it encoded here, but if you follow that algorithmic process, you are guaranteed to get a regular expression that does it. Now, one quick word of maybe advice or maybe a little tip here, and that is if you were to perform this reduction in a different order, you might get a different regular expression. It depends on the DFA, but if, for example, if we did Q1 first, we might end up with a different expression than starting with Q2 and working backwards. Or if we start with Q0 first, we might get a different expression. But they're all guaranteed to define the same language. And this is a case where if we just tried to look at this and figure out the regular expression, it might be difficult to know that we got it right. But if I follow that reduction process, I'm guaranteed, I can be guaranteed that the regular expression that I got definitively defines the same language as the DFA. Okay, so moving on here for just a second. So conversions, back to that. What about converting an NFA to a regular expression? And that, we could use the same technique for that, but we could also use the combination of the techniques we already have. We could always convert the NFA to a DFA, and then convert the DFA to a regular expression rather than going directly from an NFA. And sometimes that's preferred because NFA can be more confusing. You have lambda transitions, and it can really be in multiple states at one time. And so you could do that reduction process directly on an NFA, but sometimes it's easier on a DFA. So I'd suggest don't be too worried about that, because we could always just do the subset construction method of converting an NFA to a DFA, and then take that DFA and run it through this process to convert it to a regular expression. But either way, we now have all three parts of that triangle we can get from regular expression to NFA, NFA to DFA, DFA to regular expression. So they're all, therefore, have to be equivalent. So we now can convert any of the following. DFA already is an NFA, regular expression to NFA we did, NFA to DFA we did, and DFA to regular expression. So that proves that given any one of those, we can always convert to an equivalent version of one of the other, or of the other two. So none of the methods has any more power or less power than the others. They're all identical. The only languages we can define are regular languages, and any regular language could be defined by any of those three. So if we have a regular language, by definition, there's a DFA for it, and therefore there's a regular expression for it, because we can convert that DFA into a regular expression, and therefore we could also have an NFA for that. Or if I have an NFA, I could make a DFA, I could make a regular expression. If I have a regular expression, I could make an NFA and then a DFA. I could go fluidly between all three of those methods, any three of those methods to any of the other three. And so they can only define regular languages. Now, as we're going to see next class, there are some languages that are not regular languages. And if there are languages that are not regular, that means that none of the three of these methods will work for defining those languages. And we'll look at that next class. I don't want to get bogged down right now, and I want this to focus on those conversions. But before I let you go today, there's something fun I want to do. And that's this concept of a black box DFA. And a black box DFA, this is going to be something that's kind of for bonus and something that's just going to be fun. But the idea here is that imagine that you have one of those machines inside of an inscrutable black box. So you've got this box, and inside of it is one of these DFA machines. We know it's a DFA. We know that it has states. We know that it will take strings. Some of them it will accept, some it will reject. And we feed the string in, and it will say either yes or no. So it's kind of like a robot that we cannot see how its brain works. So we feed it a string, and it either says yes, or we feed it a string and it says no. That's the only output we have. So the challenge here is, can we figure out what the machine is actually doing inside? Can we deduce its behavior without knowing or being able to look inside it by just feeding it strings and seeing how it reacts to that? So, as an example, here's this DFA mystery machine, the black box. We feed hello world exclamation mark in, and it says accept. But if I feed in the word stonks exclamation mark, it says reject. So the question is, how does that thing work? Well, you might make up looking at these two examples, you might come up with some sort of hypothesis. You might say, well, this started with a capital letter. That one was lowercase. So maybe if it starts with a capital, it accepts. If it's lowercase, it rejects. Or maybe you'd say, if it has the same letter at the beginning, matches the letter at the end, that rejects. But if it's a different letter, H and D, it accepts. So those would be two possibilities or plausible explanations for what's going on inside of this. So I'm going to give you some additional examples here, though, for you to look at. And so the fails, quick fails, brown passes, fox fails, jumped fails, over passes, the fails, lazy fails, dog fails. So the only two that pass here are brown and over. So now you might come up with a hypothesis based on that and see maybe if you're right or not. And so what I want to do with this this kind of black box mystery is I'm going to give 10 bonus points on the midterm for the first person to correctly deduce the inner workings of that machine. In other words, if you can send me an email with your description of saying this is the description that's guiding that. In order to help you with that, you can send me an email with 5 test strings. And we'll probably do this every class you can send me. So every Monday and Wednesday, you could send me 5 additional test strings, and I'll reply back to your email with whether they passed or failed. And the first person that can deduce that and get me an answer, I'll give you 10 bonus points on the midterm. If nobody has it by the midterm, we'll extend, and that 10 bonus points will then be toward the final exam later on in the semester. So let's see what you can come up with. A couple questions to ponder, though, in the meantime. Is there going to be a way to always deduce the inner workings of a black box DFA? Is there a way you could always figure that out? And if so, could you prove that? And that's not part of the bonus. You don't have to do that, answer these questions for the thing. It's just something I want you to think about. The second question is, could you ever deduce a DFA's inner workings? And could you prove that? So maybe the answer would be yes, you could figure it out. And here's why. Or maybe the answer would be, you could never figure it out, and here's why. But you can't just say like, oh, I'm pretty sure that I could do it because I'm really smart. That's not a really good justification or a proof. Just like, I'm pretty sure you could never do that because it just seems really hard. That's not a good justification either. And thinking in terms of proofs like we did earlier in the semester, I want you to think in terms of like, what would it take to definitively prove whether or not, yes, you could always figure it out, or no, you can't. There's some of those black boxes that you could never figure out easily. So anyway, go ahead and work on that. Also, be ready for the next assignment. The next assignment, I'm going to have you do some of those conversions. That should be posted today as well. But you're going to do some conversions from regular expressions to NFAs, NFAs to DFAs, and DFAs back to regular expressions again. So you're going to do some of those conversions. So relatively short lecture today. If you're having trouble with stuff or have questions, let me know. I can always run down and have some face-to-face time if you need me to. We are going to have the midterm coming up. I'll probably announce that next class. We'll probably have that not next week, but the week after. And so be looking for that. There's one additional topic I want to get covered before, actually 1.5 additional topics before we get to the midterm. But look for that announcement either next class or the beginning of next week, so 1 week from today. All right, that's it for today. Everybody stay safe. Again, look for that next assignment. Get started on that. If you haven't finished the previous one, make sure you get those done. And other than that, wash your hands, stay safe, wear a mask if you're going out places. I really want to make sure everybody stays healthy and happy, so stay safe, and I'll see you soon.